everybody, Mr. G here today to talk about these diagrams that I've been making in previous lessons that I really have not gone over completely. It's this idea of free body diagram. And I have to say, for my classes specifically, from here on in, every single question that involves forces of any type, you better be drawing a free body diagram because it'll cost you dearly if not. So what is a free body diagram? A free body diagram shows all the magnitude and direction of all of the forces acting on an object. Okay, so generally speaking, we represent every object that we're dealing with as a box. So if it's a person, if it's a plane, if it's a car, if it's a house, it really doesn't matter. I'm not a very good artist, so I just draw a nice square box. And then from there, the force arrows will be coming out from the center. So you'll notice that anytime I've drawn a picture, and all the future pictures I'll draw, I draw them right from the center of the square, because forces act upon the center of mass, and when we have a square box, hey, it's right from the middle, right? So not a big deal. And in the direction they're coming. So when we come up with an idea like a push to the right, we're not going to put an arrow behind it because that's where we'd be standing to push. No, we're going to put it in front of it with the arrow pointing out of it towards the right because that is the way the force is acting, okay? And finally, remember that the size of the arrow indicates its relative magnitude. So when we do all these pictures, and we're going to do a whole bunch here, you're going to notice that some arrows are going to be the same length, some arrows are going to be different length. Different length means different magnitude, okay? It doesn't matter how much different they are, so long as it's a very clear indication that there are two different forces acting upon the object. So when we label free body diagrams, we're going to use these symbols more than anything, okay? And you've seen some of these before. F is just the applied force. F sub F is just force friction. Force of gravity, normal force. Force of gravity and normal force you're going to use in pretty much every case. So those would be the ones to know for sure. Tension, we're just going to do it as a capital T. Elastic force, which we'll use when we're dealing with Hooke's law, is F sub E. And then when we do, in fact, deal with air friction or air resistance, we'll just use F sub air. So these are the ones that are typical. If there's something in the question that doesn't match up with any of these, make up your own, right? Just be sure that you label them clearly so that you can identify it later on when you're trying to actually solve the question. And more importantly, if I'm trying to follow along what the heck you're doing for the math, make it clear that I know which forces are in which places, okay? So let's take a look at a couple examples here, and this first one is like the penultimate example because it's one that lots of people trip up on all the time. A box is pushed across a rough surface at a constant velocity. I'm going to put an underline on the constant velocity because what does that entail? Well, if it's a constant velocity, remember from our kinematics graphs, that's a horizontal line, which means our slope is 0. Well, what did the slope represent? It represented acceleration. So we have no acceleration, and if we then tie that into Newton's second law, what does that mean? That means that the net force is also equal to 0. So whatever forces are acting on this box, they have to be equal and opposite because they all have to cancel out. So what do we have? Well, from the center of our box, I'll go ahead and draw a floor. From the center of our box, what do we have? Well, we have the weight of the box, Fg. It's not falling through the floor, which means there has to be a force pointing up, equal and opposite, called the normal force. I'm going to do like we do in math class, just to make this a little clearer. I'm going to put little tickies to show that these are in fact exactly the same length. Okay. Well, it's being pushed across a rough surface. What does rough entail? Rough entails some kind of friction. So we're pushing at some force. Let's call this, I don't know, the applied force. And it's being pushed across a rough surface at a constant velocity. We have to have an equal but opposite force pushing back. And what one's that going to be? Well, that's going to be the force of friction. And again, these lines are also the same length. So why did we draw the picture like this? Well, it has constant velocity, which means all our net forces have to be 0, which means up and down has to be 0, and left and right has to be 0. That's why we know the force of friction is equal to the force applied. Let's take a look at a hockey player glides on a frictionless ice at a constant velocity. So again, it's frictionless, that's a key word, and at a constant velocity. Okay, so constant velocity again means acceleration equals 0 and F net equals 0. Well, let's start this off. I'll again draw the ice. From the center we have the weight. There's your Fg, and we have the equal and opposite, normal force. These two are equal. Why? Because there can't be acceleration up or down. Now, left or right? If we're at a constant velocity, we're not talking about any sort of applied forces here. The only reason we would have an applied force is if there was some sort of force acting against us, like in the previous example with the rough surface. We knew we had friction, so there had to be some sort of applied force. So in this case, well, there's no friction pushing back, which means there can't be anything applied forward, which means this is our free body diagram. So a lot of people want to think that just because we're moving forward, there has to be force applied. Again, if our net force is 0, you have to understand conceptually what this system is like before you start drawing your pictures. So let's go on to just a slew of different examples, and feel free at any point to pause this and rattle these off first before I do them. A book is at rest on a tabletop. Diagram the forces. It's at rest, which means what do we have? We have the force of gravity, and we have the normal force, and these two lines are equal and opposite. It's not falling through the table. It's not trying to move left or right, so we don't have to deal with friction, anything like that. It's just sitting there, done. Let's do another one. A girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes. All right, cool. So this box here represents the girl. She is suspended motionless. What does that mean? It means that up and down, left and right, there can't be any acceleration from a bar which hangs from the ceiling by 2 ropes. Well, let's start with the easiest one. She has some sort of weight associated with her. FG. But now there's 2 ropes that are holding on to her. Let's draw them like this. 1 and 2. And let's call these, well, it's being held by rope, so these are tensions. And it's just like that, my friends. Now, if we are sitting here motionless, what do we know about these? Well, if we call this tension 1 and tension 2, in this case, FG had better be equal to the sum of the 2 tensions, because otherwise they wouldn't be canceling out and there would be some sort of motion. So that is why she is suspended motionless. Okay? On to the next one. An egg is free falling from a nest in a tree. Neglect air resistance. That's a big one. Diagram the forces acting on the egg as it's falling. Well, an object is falling down. We have nothing pushing up on it, which means the only force at play here is the force of gravity. If there was air resistance involved, then we'd put an arrow pointing up at whatever length we needed to. But for now, that's it. In a free fall situation, my friends, all the forces, unless air resistance is included, acting on it is just the force of gravity. And that's a good thing to remember. A plane flies at a constant velocity. Note there will be an applied force generated by the engines as well as the lift force provided by the wings. Whoa! That sounds hardcore. Well, let's start with the easiest one. We know a plane has some weight. It is going at a constant velocity. So what does that mean? That means it's not accelerating in any direction, which means there has to be some sort of force pointing up. And we were told that there is this idea of a lift force. So, like I said, we don't have anything specific for it, so let's just call it force lift. And we know that these 2 lines are equal to each other. Okay, well, we have the applied force generated by the engines. Let's do that. And again, because it's going at a constant velocity, there has to be something that is equal but opposite going this way. And you know what? That is more than likely air resistance. These 2 are equal to each other. This is a case, again, of a net force of 0, which is what we see with a constant velocity. So, easy peasy. On we go. A rightward force is applied to a book in order to move it across the desk with a rightward acceleration. Consider frictional forces. Neglect air resistance. Diagram the forces acting on the book. So again, we have a whole bunch of stuff going on here. We got to consider friction, but we don't have to worry about air resistance. So what are we looking at? A rightward force applied. Here's our rightward force. Now, it's telling you that it has a rightward acceleration. What does that mean? That means that the winner is going to be this particular force right here, which means the loser is going to be that force right there. The force of friction is losing. The force applied is winning. All right? This is now a net force is traveling to the right. But do we have anything going up and down? No, which means our force of gravity and our normal force are equal and opposite. So this is an example now of an object that is moving towards the right because the applied force is much larger than the force of friction. Okay? To the next one. A rightward force is applied to a book in order to move it across the desk at a constant velocity. Aha! So now instead of having a rightward acceleration, we're going to have a constant velocity. I would hope by this point we all have clued into the idea that that means the forces have to be equal and opposite, which means if we have an applied force here, we should also have the force of friction coming back with exactly the same amount. So it's still moving, but it has a constant velocity. Okay? Onwards. A college student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram the vertical forces acting on the backpack. Well, simple. Let's say that we're staring right at his back. This is the backpack. We have a force of gravity pulling down. We have a force pulling up. In this case, is there anything pushing up on the block because of it sitting on the floor? No, which means there's only one force at play here. It's the tension caused by the one strap from one shoulder. So there it is. That's your tension. Force of gravity is your usual weight. It's motionless, which means that must equal that. There's no left or right motions described here, so we're done. Simple as that. A skydiver descending with a constant velocity, consider air resistance. Well, at this point, I think you guys are laughing at how simple these are. We have a force of gravity pointing down. We're at constant velocity, so there's got to be some force pointing up. And guess what? You all figured out by this point, it's air resistance. Simple as that. A force is applied to the right to drag a sled across loosely packed snow with rightward acceleration. Diagram the forces acting upon the sled. So this one's a bit cryptic, but the thing I want you to focus in on is loosely packed snow. We're not talking ice, we're talking snow. And anybody who's walked through snow knows it is not fun, it is hard. And if you're dragging a sled through it, it's going to slow down because there's actually going to be this friction caused by the snow itself. So if we take a look, we have our two forces again, Fg and Fn. And those are going to be equal and opposite. But in this case, we're going to have some kind of friction caused by the snow itself. But we've ended up with a rightward acceleration, which means our vector that is applied had better be larger, which means this is our vector diagram, just like that. On to the next one. A football is moving upwards towards its peak after having been booted by the punter. Diagram the forces acting on the football as it rises upwards towards its peak. So notice that it's not saying when it gets kicked, it's saying after having been kicked, which means it's in free fall. We've already been through the situation before with an egg. There's only one force on this without air resistance, and that is going to be the force of gravity. Okay? And finally, a car is coasting to the right and slowing down. Diagram the forces acting on the car. So, keyword here, coasting, and it's going to the right, and it's slowing down. Well, let's start with the easy ones. It's not falling through the road. If a car is coasting, what are you doing? Well, you're not pushing the gas, you're just letting it roll to a stop. And how is it stopping? Simple. There's some friction involved, so there's a force of friction acting on it. And that's it. A lot of people think that, again, because the object is moving to the right, that there has to be some sort of applied force. If I am not physically trying to drive this vehicle and it's just rolling, the only force at play now is just the force trying to slow it down, opposing its motion. And the fact that it was coasting to the right, which means the friction had better be pointing to the left. Okay, so crash course on free body diagrams. We've gone through a whole bunch of situations. Again, these aren't going to cover every situation, but they're sure going to cover a lot. It all comes down to you and your conceptualization of what's going on in the system and how you're going to draw that image. So good luck, and we'll see you again.